We are still on the topic of consequences of the completeness axiom. So we did the nested intervals property a couple times ago, and then last time was the Archimedean property, which is about sort of how the natural numbers sit inside the set of real numbers. The big one says that there are always really big natural numbers. Technically, for any real number x, there's always a natural number bigger than x. And then the small version was for any really small real number x, there's always some fraction 1 over n, which is smaller than x. Those two things both are the Archimedean property. The big version and the small version. What I want to talk about today is similar in spirit to the Archimedean property, but it has to do not with the natural numbers, but for the rational numbers. So the question is, how does Q, this is the set of rational numbers, sit inside R? Like if I draw the picture of R as a real line, like I usually do, where is Q in that picture? The answer is it's kind of everywhere. Not to say that every real number is part of Q, because it's not, but the rational numbers are kind of evenly dispersed throughout the entire real line. So the rationals sits, I will just write, this is informal language here, evenly dispersed throughout R, right? You can think of Q as kind of like a cloud of points that is everywhere, even though not every real number is part of Q, but the Q, there are rational numbers everywhere along the line, all right? There's a technical word for this. We say Q is dense in R. It means basically wherever you're looking in R, you're going to see some rational numbers in there. Now there's a more technical way of saying that, but I would just say the word for that is Q is dense in R. And what this means, I'll write it as a theorem, although we're not going to do the proof right away because I want to say a little bit more about this. What that means technically is for any two real numbers, A, B, and R, with let's say A less than B, there is a rational number in between. There exists, I'll call it Q, in Q, with A less than Q less than B. For any two real numbers, there is always a rational number in between them. This is the technical version of what we call dense. Q is dense in R. It means for any two real numbers, no matter how close they are together, if you have two real numbers, there's always guaranteed to be a rational number in between them. All right? This is called the density property of the rationals. Yes?
Is that like only one rational number, or is it like?
No, actually, there will be infinitely many. Yeah, because if you really do this, if you have two numbers A and B, there's a rational in between. But then you could also consider like Q and B; those are two real numbers, and so there's also a rational number in between them, and so on. So actually, there are. It's not like there's only one. There's infinitely many. But this is the density property. I remember when I was starting grad school, some guy, I was like brand new, and some guy who had an older graduate student than me, he was talking about this neighborhood has so many Thai restaurants. He said, yeah, it's like there's so many Thai restaurants there, it's like the Thai restaurants are dense. And I was like, what? And he's like, yeah, you know, like between any two restaurants, there's a Thai restaurant. That's what dense means, mathematically speaking. Between any two real numbers, there's a rational number. It's a true fact. This I want to talk about. I thought let's just try and do an example in case, I don't know if this is obvious to you. I think it is kind of, I don't know about obvious, but I hope that you agree with this fact. Anyway, let's just talk about a simple example. This is really only interesting when the two real numbers you have in mind are very close together already. And it says no matter how close together they are to begin with, there's always a rational in between them. So let's consider, let's say pi and 22 over 7. 22 over 7, you know, is like it's a rational number which is pretty close to pi, but not equal to pi. So pi is, I'm going to write some digits here, 3.14159, etc. I don't know much more than that. And then 22 over 7, if you do this on your calculator, is 3.14285, etc. So they are pretty close, and for practical matters, 22 over 7 is usually good enough if you're, say, building a merry-go-round or something. It's not good enough if you're planning a spacecraft mission, but they're close enough most of the time. Anyway, these are pretty close together. Would you believe if I told you there's another rational number in between those two numbers? I guess the pi is a little bit smaller, right? Because they agree up to this point at which pi has a digit of 1 and this number has a digit of 2. So if I were to draw them like super zoomed in on the real line, they have this arrangement. Pi is less than 22 over 7. What do you think? Can anybody name a number between pi and 22 over 7? A rational number? See, it's easy and kind of a cheat to just say, well, yeah, can I just use the midpoint? The midpoint would be whatever, you know, the average of those two numbers. You add them together and divide by 2. That's not a good enough answer because that is going to be irrational if you do that. Because you start with pi being irrational, and if you take the midpoint of these two numbers by adding them and dividing by 2, the result will be irrational because it involved the pi in there. So you can't say just take the average. That's not quite good enough. I want a rational number in between. Any thoughts? Yeah? 3.142. Yeah, that is exactly what I was going to say, actually. 3.142. Are you sure that's rational? Yeah? How do you know that's rational? Yeah. Can you tell me a fraction? Yeah. Excellent. It's 100, right? No, 1,000. Yeah, you're right. Yeah. Yes. Excellent. Yeah, so that is a rational number in between those two real numbers. Really, if you can tell what the decimal digits of your two real numbers are, then it's always easy to do a similar trick like this. You just copy the digits which agree, and then you choose some number which is in between in the position where they disagree. And then that number you turn into a fraction using a denominator of 1,000 or whatever denominator it takes, depending on how many decimal digits you're using. All right? Feeling good? Any questions about it? All right. So I would like to think about how can we do this in general, right? Like I just said, if you can see the decimal digits, then it's not really hard to invent this number. You have to have some basic idea, but once you see this little trick that she did, you can do that for other numbers. It's no problem. How could you determine that number in the middle in general? So, can we construct that number, this number, without looking at decimal digits? That's what I want to try and do. Because that's what the density theorem, this right here, it says. You have to be able to just pull this number out of nowhere, right? If you just have two real numbers, A and B, and I don't tell you what the decimal digits are. How are you going to make that happen? Well, it turns out we can use the Archimedean property, the small version, to invent that number there. So we'll use the Archimedean property. Just the way that I'm going to write the proof, it's convenient to use the small version, although you can, there's probably a similar version of this proof which uses the big version of the Archimedean property. All right, so let's try and do this. I'll write the theorem again. It says if A less than B, then there exists Q in the rationals with A less than Q less than B. All right. Now I'm going to use the Archimedean property, the small version, which says no matter how small, if you have a really small number, there's always some 1 over n which is less than that number, all right? And my really small number, so my number line, I think of this like this, and it has the a here and the b here, and we are trying to find some fraction in between, all right? Since I don't know what the decimal digits are, you can't exactly do that same trick that she suggested, but we do something with the Archimedean property, all right? The small version. So first of all, you have to start the small Archimedean property begins with a small real number x, and then you find some 1 over n which is less than x. The small real number x I'm going to take to be this distance here. So b, here's my proof, all right? B minus a, of course, is a real number. B and a are both real numbers, so b minus a is a real number, and b minus a is positive because I assume that a is less than b. All right, so when I do b minus a, that's a positive. And right away I'm going to use the Archimedean property. So then by the Archimedean property, small version, can anyone remember what does that mean? What does it say in this case? I said it out loud a few times. Starts with this. And, yeah. Yes, but instead of x, I'm using b minus a. So it's like that. This is what the Archimedean property says. There exists some n, a natural number, with 1 over n less than b minus a. All right. So this is I'm already feeling kind of good about this because on this picture, what I discovered is a fraction 1 over n, which is smaller than that distance. So really, if you think on the picture, that distance is b minus a. What we've just found is a fraction like that, which is even smaller than that distance there. All right. I feel pretty good about this because what I'm looking for is an intermediate number here, which is totally rational. All right, and this is getting there, I guess. I mean, it's a fraction, 1 over n, right? You may be tempted to just say, can I just use as my answer a plus 1 over n? That would be just like whatever point lines up right there. That's is that a rational number in between? Any thoughts about that? 1 over n is a rational. A plus 1 over n would be right wherever this point ends up there. What do you think? He thinks it's rational. Do you agree? Yeah, right. The issue with that is a may not be a real number, and in which case, if a is irrational and you add 1 over n, it's going to be irrational. And so actually a plus 1 over n is not good enough for an answer, unfortunately. You got to do an extra little trick, but it's not so bad. Check it out. Right here, I'm going to multiply through by n. All right. So 1 less than, I can say nb minus na, right? And now what we have here is two numbers, n times b and n times a. You can think of this as if over here I just blow up this whole picture. So multiply everything by n here. What you're looking at now is nb and na, right? But they're no longer super close together. In fact, they are kind of far apart because here, what this says is the distance between nb and na is more than 1. So the distance apart here is greater than 1. Question about that? No. Sorry, that's a mistake. Thank you for that. It should be NB is bigger. Thanks. Yes, they definitely should be in this arrangement now. But what I'm saying is that distance there is now greater than 1. Yeah.
So why exactly is A not a real number?
It's not rational. It is a real number, but it may not be rational. And the thing is, this number we're trying to end up with in between, we need it to be rational. And if a is irrational and you add 1 over n, it's still going to be irrational. That's the problem with a plus 1 over n. All right? But What I'm saying is, these two numbers now, they are no longer super close together. They are fairly far apart. Further than distance 1 apart, what that means is, so there is a I'll say it this way, there's an integer in between. That's because we're talking about two numbers where the distance in between them, here it's this distance here is, I'll just write it in words, more than 1, right? And I hope you agree, if I have two real numbers and they're further than distance 1 apart, it means there's a whole number in between them, right? And this, so I will call it, say, m is in between NA less than NB, all right? Right there, m. Those two numbers are far enough apart that there must be a whole number in between them. Their distance apart is more than 1, all right? And we're almost done here. Remember what we were looking for? Anyone see how to finish it off? We are looking for, this right here is actually looking very similar to what we want to end up with, is that, right? Any idea? Yeah?
Divide by n.
Yeah, divide through again by n. I started by multiplying by n, then you do some little trick, and now I'm going to divide the n back out, and I get, so divide by n, and now it says a less than m over n less than b. And this is exactly what we wanted, all right? It is a rational number in between a and b, all right? So it's really just the Archimedean property, the small version, plus an extra little trick about multiplying everything by n and then dividing everything by n, all right? Any thoughts about that? Any questions? Is this a mind-blowing theorem? I'm not sure. I think probably everyone, I don't know if you ever have thought about this, but probably if you think about it a little bit, you will realize, yeah, there must be a rational number in between any two irrationals. Is it true that there's an irrational in between any two rationals? Yes, that is also true. For instance, if you're just talking about decimals, like what if I gave you, I'll just make up two decimal numbers, 4.0s. How about 4, right? And then also 4.1, now let's make it even closer. 0, 0, 1, 1, 1, 1 repeating. Those are two rationals. Can you give me an irrational that's in between them? Yes, you can. This is a little weird, but an irrational in between them would be something like 4.000, 1, 2, 3. No, I'm going to go. How about this? 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. That's a silly number which never repeats its decimal expansion. It does some other weird pattern with the decimal numbers, but that is irrational. I don't know if you believe me, but every rational has a repeating decimal expansion or terminating. This one does not repeat. It does this stupid thing with the 1, 2, 3, 4, 5s. All right. So, and it is in between the other two. So it's a fact. The rationals between any two reals is a rational, and it's also a fact between any two rationals is a irrational. All right. Any thoughts about that? Great. Let's move on to a little something else. This is our last big consequence of the completeness axiom, and this is a big one. Actually, this thing that we're going to talk for the rest of today and some tomorrow about, this really kind of blew my mind when I first learned this as a young lad. I want to talk about the cardinality of the set of real numbers. I don't know if this is something you've talked about in your other classes. I think probably not. It is absolutely a mind-blowing fact, which I have, in my opinion, is like profoundly beautiful, and I have tried to explain this to some non-mathematical people with limited results. I hope that you will feel that it's as interesting as I believe. This is about, I'm gonna give you a little bit of history behind this because it is such a profound idea, in my opinion, in the history of mathematics. Very important This is about the size of R. Size meaning how many elements are there in the set of real numbers? How would you answer this question by asking how many real numbers are there? Yeah, infinity is really the only sensible answer to this question. I would say there are, grammatically speaking, I would say there are infinitely many real numbers. We don't usually say there are infinity real numbers, because I don't know why. That's the grammar of the word infinity. But yeah, the size of R is infinite. There are infinitely many real numbers. How many natural numbers are there? Also infinitely many. This is not a trick question. So, does that mean that there are the same number of natural numbers as there are real numbers? I don't know. It seems to me there's like more real numbers than there are natural numbers. Because I can draw a picture. I can kind of see the natural numbers go one after another, whereas the real numbers are sort of packed in there, right? All of these are what this little next couple days we're going to talk about all of these things. So this word, cardinality, is a fancy word which just means the number of elements. Although maybe I shouldn't use this, it's not always a number, because sometimes the cardinality is infinity. So it means the size of the set, which sometimes could be a number if your set is finite. For example, the cardinality of this set, 5, 6, 7, 8, is, what do you think? 4. Yes, someone's shown me with the hand. Yeah. All right, the cardinality of that set is 4. All right, but the cardinality of, say, this set is, I would just say, infinite. Right? You could say the cardinality equals infinity. That's a typical way that we talk about this. But I'm here to tell you these sets, N, Q, R, which we like to talk about a lot. On some level, you should probably feel like N and R is kind of bigger than N. But if you really believe that, then what you're saying is that there are like two different sizes of infinity. There's the smaller infinity and the bigger infinity. And then what about this one? Is that yet a third size of infinity in between the other two infinities? Or maybe for some weird reason, maybe these two are actually the same size, or maybe these two are actually the same size. All of this is mathematics that was first explored by a guy named Cantor in the 1870s. And so Cantor, this is a big name in those days, 1870s, investigated the cardinalities of various infinite sets. And Cantor did discuss these three sets, the natural numbers, the rational numbers, and the real numbers. And Cantor discovered there are different sizes of infinity. It's a true fact, and by next time you will have seen a proof of this. And it's actually not so hard to do. I mean, it was a major breakthrough when Cantor had this idea, although once you have the idea, it's not so hard to formalize everything. But anyway, it is a true fact. There are different sizes of infinity. So when somebody says to me, I'm imagining an infinite set, I will naturally, in the back of my mind, wonder, what infinity are you talking about here? Is it, you mean infinity like the natural numbers is infinite, or do you mean infinite like the real numbers is infinite? Or maybe some other, or maybe the rationals, infinite like that one is. Turns out, this is kind of a surprising fact, of these three sets, actually there are only two different sides of infinity represented here. Q is equal in size to one or the other of these. I don't want to give it away just yet, but it turns out that the size of Q is infinite, but that size of infinity is equal to one of the other two, all right? Very strange and interesting fact, in my opinion. There are different sizes of infinity. I don't know if anyone's wondering, how many different sizes of infinity, if you were to guess? What do you think? What do you think? Infinitely many? Yeah, actually, it's true. There are infinitely many different sizes of infinity. Anyone have a follow-up question? There's a very deep follow-up question to that. Yeah? Okay. I know it's a lot to take in. Yeah, this is something that nobody talks about this in a calculus class, even though you do talk about like lim x goes to infinity all the time in a calculus class. Nobody mentioned it at the time, but that infinity always refers to this size, because in a calculus class, you're always talking about x as a real number and it like goes all the way out there. What you mean is it increases through without bound inside the real number. So that infinity basically is this size, not these other two. Anyone have a deep follow-up question to the statement that there are infinitely many different sizes of infinity? The deep follow-up question, yeah?
What size infinity?
Yeah. Yeah, when I say there are infinitely many different infinities, which infinity do you mean when you say there are infinitely many different infinities? Like, are there this many, or are there this many, or are there this many, or something else? The answer to that question is actually very, very technical, but the short answer to that question is the number of different sizes of infinity. There are infinitely many of those, and there are more of those than any of the sizes of than any individual size of infinity. Think about that. Yes? Yeah, so this opens up many interesting playground conversations, such as, can I do like infinity plus 1? Is that a thing? Is infinity plus 1 like the next biggest size of infinity? Or can I do infinity plus infinity? Or can I do infinity times infinity? All of these questions, actually, there is real mathematics behind, and there are real answers to all of those questions. This is called, what I was just describing is referred to as transfinite arithmetic. That is adding and multiplying things which are, these sizes are not numbers, they are called transfinite cardinalities. Another question?
Does the size have refer to the number of elements
Yeah.
in the set?
Right.
Okay.
Yeah. So you think like this n, there's infinitely many, but kind of not so many. Whereas this r, there's infinitely many, and there's like really a lot, really a lot, infinitely many. Yeah. And the q, who knows, right? It's in between. Actually, it's not in between. Actually, we're gonna know. So let's try and talk about some of the details. Actually, I want to give you I don't know who cares about the history of this, but I think it's interesting. Cantor basically did this in some papers in the 1870s, and this was very, very controversial at the time. So around, when Cantor did this work, around the 1870s, mathematicians didn't like infinity. They would have said that infinity is an abstract concept, like when you say lim x goes to infinity, they would say that, but they would write that down, but they wouldn't, they would be very forcefully saying that infinity is not a number, which we still do say that. And when I write this, x approaches infinity, actually x is not approaching any specific thing, it's growing forever. So this right here is just a notation which means x grows forever. It doesn't actually mean that it approaches something. So mathematicians at that time thought of infinity as like an unapproachable idea And they never talked about infinity as a concept by itself. It was just a shorthand for the purposes of writing this. But infinity as a concept by itself was not viewed as legal. So they would have said at the time, this is like philosophy, or even worse, theology. Actually, this is not a joke. Many mathematicians were just very uncomfortable with the idea of trying to talk about infinity. There were people like who said that Cantor's work was trying to like kill God or something, or like overanalyze. There was this like moral idea that we should not try to analyze infinity mathematically, because I don't know. I disagree. I'm not a opponent of talking about God, but I'm totally cool with talking about infinity also. All right. But Cantor was a Christian, and he said to them, like, hey, I'm just, I'm following the mathematics where it goes. And Cantor said, like, I believe that God made us, and part of why he made me is to understand mathematics. And this is what I'm doing here. So I'm not killing God, right? This is like, I am a true servant of God by discovering that there are different sides of infinities. It was quite controversial for a while, but by like 1900, this was basically, everybody was on board with this. And it became one of the major reasons why all of mathematics in the 20th century became phrased in terms of set theory and sets. Cantor's work was one of the major kind of works of mathematics which was just about sets. Before then, sets had been used. You talk about sets every so often when you're doing a calculus problem or something like that. But Cantor was talking about sets just by themselves, and it was a big deal. So that's the little historical introduction. Sometimes when I'm talking to people talking about God, sometimes people say to me, "Oh, nobody can really understand God because God is infinite. You can't understand something that's infinite." And I want to say, like, the mansplainer in me wants to say, like, well, actually, there are actually a lot of things that you can understand about things that are infinite, and there's a lot you can say about things that are infinite. Anyway, I'm into it. This is now referred to as, these are called transfinite set theory or something like that. Transfinite cardinality, that sort of thing. This word transfinite means when I'm talking about different kinds of infinity as if they were different numbers. There's the smallest infinity. That's something that I didn't, that's another kind of deep question. I kind of said there are infinitely many of them, and there isn't a biggest one because there are always bigger and bigger infinities. Is there a smallest one? Actually, the answer to that is yes, there is a smallest one, and it's n. That's the smallest infinity. There are no smaller ones, but there isn't a biggest one because there are infinitely many of them, many more than you could imagine. All right, let's talk about this. So, how did Cantor? Cantor had his sort of big idea was just the idea of how can you measure two different infinite things and compare their sizes, all right? How can you tell if I present you two different infinite things, how can you tell if one is bigger than the other one, even though they're both infinite, all right? I'll tell you the very basic idea, and this you can explain to your friends at dinner tonight, how you can compare the sizes of two infinite things. For example, if I were to ask you, you can ask your friend, how about, I'm going to draw for you some people. I got 3 people and 3 houses. All right. And I ask you, even your stupid friends at dinner can answer this question. Are there the same number of people and houses? All right. The answer is yes. How do you know that? There's a normal answer, and then there's a super sophisticated Cantor answer. The normal answer is there are 3 of each. That's the same. 3 people, 3 houses. How do you know that? Because I counted them. 1, 2, 3. 1, 2, 3. Does anyone have a different way of explaining why there are the same number? See, the obvious problem extending this to infinite sets is you can't count them all. If there's infinitely many people and infinitely many houses, you can't just say, yeah, I counted them up, infinity, and then down here, infinity, so they're the same. There's another way you can demonstrate that there's the same number, even if you're not capable of counting. Or maybe your friend says, you know what, I never learned to count up to 3. Can you make it work for me, even without counting to 3? Yeah.
There's the same number of houses.
Yes. How do you know that? Without counting them up. That's the thing. Yeah?
One person for each house, like, pairs.
Yes, you can match them up like this. Match them up. And everybody matches, every person matches with one house. Therefore, there are the same number of people in houses. And you can do that even without counting them all up. This is Cantor's basic idea. Super deep. It's not all that deep, but it's I mean, you have to be kind of deep to think of this. All right. So what this whole thing is about, we'll measure sizes of these sets by matching up elements. All right. And if you can describe how to match things up, now they have to match up in a particular way, like in this example, every person has to match with one house, and every house has to be matched with one person. You don't want to bunch them up. Like if I make 2 people match with one house, then you mess up the count, right? So every one thing up there has to match up with one thing down here. This actually, when we do this mathematically, we think of this as a function which takes each person as the input, and it tells you which house they belong with. All right. And the function that I make here, I am requiring that every single one of the people matches up with only one house, and I don't miss any houses, and I also don't miss any people. There's some words for that with functions. Yeah.
Have you changed the matching to help with the system?
Yeah, like this is not the only way you could have matched up the people with the houses.
If you have like one person and 2 houses, if every one person has 2 houses.
I mean, you can do that, but that would not demonstrate that there's the same number. Like if I had, two people and 4 houses, and I say, oh yeah, one person gets those 2, one person gets those 2. I mean, they're matched up, but you are not demonstrating that there's the same number of people in houses anymore, which is what we're trying to focus on. Yeah. I suppose you demonstrated something here, but it's not about the number of the sizes of these sets. All right. So anyway, we're going to do this with functions. So let's get a little technical here. So given 2 sets, x and y, these are 2 sets which I intend to compare the sizes of. They may be finite sets, but it's more interesting when they are infinite sets. We need to build a function which I will write like this, f x to y. What that means, I hope you remember this from like your discrete math class, that means f is a function whose domain is the first set, x, and the codomain is y. All right, this is the domain. This is the codomain. All right, and in order for this to be a legitimate sort of matching, which shows that the 2 sets have the same size, you need for, first of all, none of, like in this example up here, none of the houses get missed, right? Every person has to go to a house. Anybody remember, there's actually a word that you already know for that. I'm talking about a function here where all the points in the codomain actually have a value. That's, anyone remember the word? Yeah? Yeah, 1-to-1 is something else. Onto is the other one. Yeah. Onto means, so given sets like this, we build a function like this, and x and y have the same size. If f is onto means that nothing in the codomain is missed, and It also has to be the case that every one person goes to a house. It's not like two people go to the same house. Remember what that's called? That is called one-to-one. Yeah. So onto and one-to-one. All right. And this was Cantor's big idea, which no one had thought of that before Cantor. And before Cantor, everybody sure would have agreed with you that this is true. But the big idea is just the fact that you can do this even if the sets that you started with are infinite rather than finite. X and Y have the same size if F is onto and one-to-one. Some other words, I don't know if you've heard these languages or these words. If you use this language, onto is also sometimes called surjective, and one-to-one is called injective. And does anyone remember the word for if it's both of them? Yeah, then if it's both of those, which is what I want it to be, one onto and one-to-one, is bijective, or that's the adjective verb, or the adjective version, or you could say as a noun, F is a bijection, that's what I'm usually going to call this. Onto and one-to-one both is called a bijection. All right. So just a little review. I don't know if how into these things you are at this point. You may have forgotten this since discrete math. For example, if I have x and y, let's just write them as if they were finite sets. And you can think of this as sort of like a dots and arrows kind of a diagram. I'm going to illustrate a function here by drawing a bunch of arrows. What about arrows like this? So this means this point, f of this point goes to there, f of this point goes to there also, f of this point goes to there. Is this one-to-one? They are saying no. Why not? It's because these 2 points go to the same. So this is not one-to-one. Is it onto? Onto means that every point in the codomain actually gets hit by one of the arrows. And the answer is no, it is not onto. Not one-to-one, not onto. So this function is not a bijection, if I call it f here. So this f is not a bijection. And so this particular function does not demonstrate that x and y have the same size, although the x and y do have the same size, but it's just that function is not good enough to demonstrate. How about, what if I had something like this? How about that? Another function here. Is it one-to-one and is it onto? What do you say, one-to-one? The thumbs or nod? Yes, it is one-to-one. And it is not onto because I missed one of the points over there. All right. How about, these are simple examples just to make sure everybody still remembers how to do this. How about this function? Is it one-to-one? Is it onto? The answer is yes and yes. This one is one-to-one and onto. It is one-to-one and onto. So it is a bijection. Bijection. All right. This is how we're going to measure the different sizes of infinite sets. So I'm going to write this as a formal definition, although it's more or less what I've already said. I'll say two sets, A and B, have the same cardinality when there exists a bijection F A to B. That's what it means to say they have the same cardinality. And cardinality is a fancy word for just how many elements, all right? The cardinality sometimes is a number, sometimes is a transfinite cardinality. Yep. Yes. Yeah, right. That's right. Yeah, so the sets are the same size when there is a bijection. Now, in this example, this function that I wrote is not a bijection, but there is a bijection. It's just not the one that I wrote down. Actually, this one down here is a bijection. There are many others. You could just go, each point goes straight across. That is a bijection. So they are, that one right there is not a bijection, but there is another bijection we could do. All right, we got 4 more minutes. Let's just do a specific example here. This will only take maybe 1 minute. How about the set of even numbers and the set of odd numbers? Let's just look at positive numbers. So I'll call A 1, 3, 5, 7. These are infinite sets, and B is 2, 2. Ready? 2, 4, 6, 8. These are 2 infinite sets. Do they have the same size or not? Their size, each one individually, is like infinity, but are they the same size or not? To answer this question, you must demonstrate a function which matches them up, one to the next, or somehow prove that there can be no function which matches them up. In that case, there are different sizes. Actually, they are the same size. So we want a bijection that goes domain A and codomain B. Give me like a formula here. F of x equals, I want a function which somehow transforms all of these numbers into these numbers. What do you think? X plus 1, yeah. Is that a bijection? It is. We'll do some more practice next time of proving things are bijections, but that is a bijection. Probably you remember maybe a bijection, a function is a bijection if and only if it has an inverse function, and this does have an inverse function. You can go back the other way by subtracting 1, right? Plus 1 or minus 1. All right, so the set of even numbers and the set of odd numbers, there's the same amount. How about this? That seems pretty obvious to me, actually. Here's another example. How about, and this will be where I'll leave it. How about A is 1, 2, 3, 4. This is etc. This is the set of natural numbers. B is 10,001, 10,002, 10,003. Right? What's interesting about this is B is, would you agree? B is a subset of A. A is all natural numbers, starting with 1. B is like only some of them, right? It's the natural numbers, but only starting at 10,001. You skipped over a bunch of them. Are these two sets the same size? Can you think of a function which goes one to the other? I think actually I can. You got anything else? Yeah. X plus 10,000, yeah. So, the moral of the story is transfinite cardinalities are kind of weird. In this case, A is a subset of B, but actually they end up having the same size after all. So their sizes are both infinite, but they're the same size. This this somewhat silly example I wanted to mention. This is the only, to my knowledge, the only old school church hymn which includes a verse about transfinite arithmetic. Is in this thing here. Those two sets have the same size. The last, I don't know if you know, this is my favorite hymn verse ever. The last verse of Amazing Grace is about when we all die and go to heaven, we're going to be there a long time. And it says, what it says is, when we've been there 10,000 years, bright shining as the sun, we've no less days to sing God's praise than when we first begun. Meaning, after you've been in heaven for 10,000 years, the remaining duration for which you will be in heaven is actually the same as when you started. That's kind of like saying these two infinite sets are the same size, right? Yeah. All right, much more on this next time.